Okay, good morning, guys. Today, like we talked about the other day, we're going to continue with applications of the integral and applications of the sort of convergent stuff we've been talking about by moving from the question of arc length to the question of surface area. And then at the end of class today, if there's time, I'm going to give you a little introduction to where we're going to be going next week. So while people are filtering in, I want to just take a second and remind you what we did last time and sort of show you how we're going to move forward from there. This, of course, is MAC2312, section 002. It's a lecture, and today is the 20th. You may notice that we have an extra person in class today. Professor Joe Mosel is with us, observing for the day. But don't be shy. So what we're going to be doing today is extending our work on arc length to a result on surface area. Okay, and we'll be working in the same sort of setting that we were working in section 8.1. So this is going to be section 8.2. And just a reminder of where we're going. After we cover this section, we're going to be jumping to 10.1. And then the last few sections that we're going to cover are 10.1 through 10.4. And we'll begin those next week. Last time, remember we said if we take a function f of x and we want to find the length of that curve from A to B, so you kind of think of this as a rope. If you could pick that rope up and stretch it out straight, then what would the length be from this point to this point? We saw that the arc length, and the standard notation for that is S, is the integral from A to B of the square root of f primed of x squared plus 1 times dx. And we got there, remember, by kind of thinking about something like a Riemann sum. We chopped the interval AB into a bunch of subintervals and then looked at the straight line distance between a bunch of points along that curve. And then in the limit, as n went to infinity and each one of those little curves got shorter, our approximation became exact. And that formula happened to be a perfect Riemann sum for this integral. So as n went to infinity, we got this integral. Before we dive into the surface area stuff today, I just want to talk about a little bit of notation. You guys remember when we did all of those area and volume problems at the beginning of the term, I would use dA for the little piece of area, or dV for the little piece of volume. Well, here, when I want to talk about a little piece of arc length, I'm putting littles in those quote bunnies to say I'm not totally responsible for the word little. We mean like differential length, really, really tiny. I'll use the term ds, right? Because if s is the overall arc length, then a little ds is the thing I'm integrating to get s. And ds, of course, is the thing that you integrate to get s. So it would be the square root of f primed squared plus 1 times dx. So it's all the same sort of logic that we used to connect dA to A or dV to V at the beginning of the semester. Today, what we're going to do, this is going to be an instrumental piece in coming up with the surface area for a solid of revolution. So I will redraw this picture in greater detail in just a second, but the basic game is this. I want to take this region the region bounded by f of x from x equals a to x equals b, and rotate it about the x-axis, just like we did back in chapter 6, that's going to generate a solid with a certain rotational symmetry. And to find the surface area of that solid, I'm going to imagine taking a little tiny piece of arc length, like this. And just rotating that little tiny piece of arc length will generate a little tiny piece of surface area. Then I'll integrate that little tiny piece of surface area to recover the whole surface area. All right, so just a recap from last time, what we did, and the labels we're going to use. So this little tiny element of arc length, I will call d. All right. Any questions? Anyone need reminders about this notation? Anything that's bugging you about these? Okay, then let's jump in. I'm going to redraw this picture a little bit bigger. We're going to imagine actually rotating this region, and we're going to talk about that solid and get a formula for its surface area.
Oh, sorry, can you just bring up that page one more time?
Sure, yeah. Yeah, I know folks are still kind of trickling in, so if you want to take a second to jot this down, that's okay.
Thank you.
Okay, I am going to move on now. My art skills hopefully won't let us down too badly, but I'm going to do my best to draw this in a nice way for you guys. So here's your function f of x. I want to take this function and the region it bounds from x equals a to x equals b and rotate that about the x-axis. We did lots of this earlier in the term. We know that this is going to generate a solid whose cross sections are circular. I'll do my best to draw the solid here. Maybe I'll draw it in here, actually. So this solid will look something like this, right? Kind of like a flower vase. And I'll draw this side being solid so we can sort of see it in 3D. All right, if I rotate the region bounded by that curve about the x-axis, then I'll get a solid looking something like this. And normally when we want to define the volume of this solid, we imagine rotating just a little strip of area and then get the little volume from that, and then we integrate that little volume to get the total volume. Here, because what I'm after is the arc length, instead of rotating a little strip of area, because what I want is surface area, instead of rotating a little strip of area, I'm going to rotate a little strip of arc length. So in pink here, you see that ds strip. And I imagine what happens if I rotate just that? Well, then I'll get this little band that runs all the way around my solid. And if I take ds to be small enough, then I can imagine that the edges of that band are flat. That's the kind of crucial thing here. The surface area, the little bits of surface area that I get here, this tiny little strip of surface area, I'm going to call dA. So let's just redraw that band over here. Remember that ds is the square root of f primed of x squared plus 1 times dx. So if I take just that little band, on its own, and we do the same thing we did with the cylindrical shells method, where we're going to cut this and unroll it. So if I bring my very sharp scissors through here, snip this thing and unroll it, it will unroll into a nice tall rectangle. This dimension of the rectangle is coming from this dimension of the band. And what is that in my picture? What is this little distance here of arc length along the curve? It's ds. So this is ds. Remember, my goal here is to get the area of this pink band so that I can then integrate that little area for the full surface area. So I need two things. I need this dimension and this dimension. This dimension is this dimension, which is coming from this little piece of the band, which is ds. What is the relationship between this dimension and the geometry here? If I imagine my axis of rotation poking through here, what does this look like in relationship to this object, whose cross-section here, remember, is a circle?
Its circumference?
Yeah, perfect. It's the circumference. This thing here has a radius. And when we cut and unroll that, the length of the resulting strip is the circumference of this circle. Okay, well, that radius in the bigger picture is this distance, right? It's the distance from my axis of rotation out to the boundary here.
The equation for the circumference of a circle.
So the circumference of a circle, remember, is 2 pi times the radius.
Circle is 2x pi xr.
The definition of pi is the ratio of a circumference to its diameter. The diameter is twice the radius. So the last thing we need to answer is, in terms of this big picture, what is the radius? If I can plug that in here, I'm in good shape. So if I'm at an arbitrary point x, where I'm sort of doing my slice, what is this distance from the axis of rotation up to my curve, assuming that the axis of rotation here is the x-axis?
F of x.
Good, it's f of x, because this point right here is x comma f of x. So r is f of x. Which means that the circumference, 2 pi r, is really 2 pi f of x. Now, if my axis of rotation was something else, if this function was not a function of x, then this would be something else. But in this setting, which we understand well, the little surface area strip has dimensions I'll call this dA for little differential area, differential surface area, has dimensions 2 pi f of x times ds. But ds, that's my little unit of arc length. That's the square root of f primed of x squared plus 1 times dx. So the thing that I need to integrate to get the surface area is this, which, let's be honest, is a little bit scary looking. It turns out to be good news in a lot of ways. Remember, some of those arc length integrals where you just had to compute this thing, the integral of this, were tricky because the thing inside here, you want to make a substitution, but you don't have the piece outside you need for the differential. Well, this can sometimes contribute that piece you need. So there are situations where the surface area integral is actually easier to manage than the arc length integral. Let's write down what we've just discovered. That the surface area A, it's the integral of dA, it's the integral from A to B of dA, which is the integral from A to B of 2 pi f of x times the square root of f primed squared plus 1 dx, where this piece at the end here we call sometimes ds. So this is the surface area of the solid of revolution that's generated by rotating the region bounded by f of x about the x-axis. And we're looking at just the x values between A and B. So I think the best way to start wrapping your head all the way around this is to just look at some examples. Some of these examples are terrifying, and some of these examples are surprisingly simple. You all know what the surface area of a sphere is, but what happens if you chop the ends off? So let's find the surface area of the solid generated by rotating the region bounded by y equals the square root of 4 minus x squared from x equals -1 to x equals 1 about the x-axis. I know there's a lot of word soup in these problems, but let's be patient. First, we need to know what this thing looks like. If you square both sides here, you get y squared equals 4 minus x squared. You add the x squared over, that's x squared plus y squared equals 4. So that is a circle of radius 2. And since here this is solved for y, and we only have the positive square root, not plus and minus, we don't actually get the whole circle, it's just the upper semicircle. They want us to take the region just from -1 to 1, which is this, and rotate it about the x-axis. So the solid that we get here kind of looks like a wedding band, like a really fat wedding band. Let's see, my art is bad and I feel bad. But yeah, something like this, right? Where these sides are flat. So if I were to rotate just this region about that axis, I'll get a solid that looks about like this. The question is, can I find the surface area of that solid? So I need to compute all the little pieces that go into this integral and then try to actually evaluate the integral. I begin by finding my little arc length element ds. ds is the square root of f primed of x squared plus 1 times dx. F of x is here. So we'll need to compute f primed. F primed of x is the derivative of f of x, and you can write f of x there as 4 minus x squared to the 1/2 power. So f primed is the derivative of that, which is a pretty straightforward chain rule derivative. The 1/2 comes down. You get 4 minus x squared to the negative 1/2. And then by the chain rule, you need to multiply by the derivative of the inside. The derivative of 4 minus x squared is 0 minus 2x, or just negative 2x. This can be written more nicely. This 1/2 and this 2 will cancel. This is 4 minus x squared to the negative 1/2. So there's a square root of 4 minus x squared downstairs. And then upstairs, I have negative x. So that's f primed. I can plug that apparatus in here. But let's go ahead and write down our full surface area formula, and we'll plug everything into that. So I know that the surface area here should be the integral from a to b, from -1 to 1, of 2 pi f of x, which is the square root of 4 minus x squared, times ds, which is the square root of f prime squared. So I'll take this and square it, plus 1, all times dx. So this is the integral we need to compute. And at the outset, it looks pretty intimidating. But the algebra here is going to be quite nice. When we square this, the negative here will go away. The top will just become x squared. And in the bottom here, I'm squaring a square root. So the square and the square root will annihilate each other. And I'll just get, let's pop out the 2 pi, integral -1 to 1. I've got my 4 minus x squared under the square root up front here. That's this piece. And then here, if I square this, I get x squared over 4 minus x squared. All of that is under the square root with that plus 1 still chilling. Everybody comfy so far? These guys are being multiplied. Now you remember this rule. You have the square root of one thing times the square root of another thing. You can treat that as the square root of the product. We use this going in both directions all the time. So I'm going to take those two square roots, which are being multiplied, and write them as a single square root with the product inside. So I'll have one big square root, and then inside there will be 4 minus x squared times x squared over 4 minus x squared plus 1. And all of this is under my big radical here. Now, for my money, the easiest way to simplify the apparatus under the square root here is to leave this as a single piece. Think of 4 minus x squared as a single piece, and then think of this as two pieces, this plus this. Because when I distribute 4 minus x squared, this one chunk, over this thing, I'll get 4 minus x squared times this fraction, and the 4 minus x squareds will cancel because it is a factor of the bottom and a factor of the top. And then over here, I'll just have 1 times 4 minus x squared. So continuing with the algebra, we have 2 pi integral -1 to 1, big radical, 4 minus x squared times x squared over 4 minus x squared. You can think of this as being in its little parentheses down here, times 1. This and this will cancel, and I'll just get the numerator, x squared. And then 4 minus x squared times 1 will just get me 4 minus x squared. And that big, scary looking integral turns out to be a constant. X squared plus 4 minus x squared, that's just the square root of 4. Which on a good day is 2. So I can pop that 2 out of the integral. 2 times 2 pi is 2 pi. Integral -1 to 1 of dx. So this is where we land after doing all the algebra. Integral of dx is trivial. This is 4 pi times x evaluated from -1 to 1. And 1 minus -1 is 2. So this is 4 pi times 2, or 8 pi. So the surface area of that fat wedding band shape here is 8 pi. If you wanted to, you could do this integral from -2 to 2, and that would give you the surface area of the whole sphere, because remember that sphere was of radius 2. Questions on this one? Is there any step here that we'd like to look at a little more carefully? Questions about the formulas or derivatives or where things came from, where they went? Can everybody sort of visualize this solid that we get by rotating this region from -1 to 1? So the sides would be flat, but the top would be curvy. So here's that curvy top, and these are the sort of flat sides. Yeah. Yeah, no problem. Okay. Yeah, so I am going to go ahead and mute everybody by default. If you do need to talk, you can hold the space bar. Remember, think of it like a walkie-talkie, say push to talk thing. If everybody is comfy with this, I'm going to move on to a slightly more challenging example. So last call for questions on this fellow. Okay. I always really liked the idea of rotating this little piece of arc length to get a little piece of surface area. Something about that was just so satisfying. For our next problem, I want to begin with a curve that everybody knows well. Let's find the surface area of the solid generated by rotating the region bounded by y equals e to the x from x equals 0 to x equals 1 about the x-axis. Okay, so I want to find the area of the solid generated by rotating the region bounded by y equals e to the x from x equals 0 to x equals 1 about the x-axis. So we'll draw the picture here. Y equals e to the x, we know looks like this. All right, he settles down on this horizontal asymptote as you run off to the left, and he gets very large very quickly as you run off to the right. X equals 0 is right here, and we'll say x equals 1 is right here. So the region in question is this region. And I'm going to rotate it like this. So the resulting solid, let's see if we can do a decent job with this. The resulting solid is this kind of horn shape. It's neat, right? It's like you took the end of a trumpet and cut it off. And what I would like to do is find the surface area of this solid, not including the end, the caps here, right? Just the surface area of the stuff in between. So I'd like to find all of this surface area. The game here, just like it was in the previous problem, is to imagine rotating just a little element of arc length. Sorry. So if we rotate just that little element of arc length, we know that the little area we'll get is 2 pi f of x times ds, where ds is the square root of f primed of x squared plus 1 times dx. So we'll need to compute this ds, this little arc length, and then multiply that by 2 pi f of x and integrate from 0 to 1. Here, since f of x is e to the x, we don't need to think too hard about that derivative. F primed is also e to the x. That'll be e to the x all squared plus 1 dx. That's my ds. So the surface area A is going to be the integral from 0 to 1 of 2 pi f of x, which is e to the x, times ds, which is this square root. Times dx. Now, it's been a while since you've seen an integral like this. Does anybody have an idea for how to proceed from here? Does anybody see something that they would like to do to this integral? Who can help me out? Try to think back to test 1.
Could you do IBP?
IPP is not a bad idea, honestly, looking at this. Yeah, you've got a clear product here, right? So maybe you want to integrate this and differentiate this piece. You could jump into this with IBP. It's not the path I'm going to take because I think there's something that will make it a little bit easier to sort of see where we're going to end up. But you absolutely could jump in with IBP. Does anybody see something else? Caleb?
Trig sub?
Trig sub is going to happen eventually. Yeah. What are you thinking for the trig sub?
To like get rid of the square root.
Yeah. Now remember, my trig sub Bible says if I've got a square root of like z squared minus 1, then I want to substitute z equals secant theta. If I've got a square root of 1 minus z squared, then I want to substitute z equals sine theta. And if I had a square root of, 1 plus z squared, or z squared plus 1, then I would want to substitute z equals tan theta. Now, underneath my square root here, I've got e to the x being squared. This kind of looks like this guy. And you could jump in here using the substitution e to the x equals tan theta. But I think the most natural thing to do is to make a little substitution before the big one. Make a little u sub or z sub. I'm going to pop out the 2 pi, and then I'll have integral from 0 to 1. I'll write this as e to the x squared plus 1 times e to the x dx. So I'm writing it in this way to be kind of evocative of the substitution I think we should make at the start. Anybody see it? Just a little u sub that we could do here, a little z sub.
E to the x.
Yeah, let's do that. I think this makes it a bit easier to see which trig sub we'll use down the line. And you're correct in saying you could use IBP, but I think it'll be easier to see what the outcome is if you go through the two substitutions first. So if z is e to the x, then dz is going to be e to the x dx. That's why I brought that over here. What else must we do every time we make a substitution?
Change the bounds.
Yeah, beautiful. So when x is equal to 0, z is e to the 0, which is 1. And when x is equal to 1, z is e to the 1, which is e. So this will become 2 pi integral 1 to e square root of z squared plus 1 dz. And I think from here, it's a little bit easier to see the next move. What's the next move?
Now use the trig sub.
Good. Specifically what?
Tangent.
Beautiful. Yeah, the constant here, a squared is 1, so a is 1, so we'd sub z equals a times the tangent of theta, but that's just 1 times the tangent of theta. dz is going to be secant squared theta d theta, and again, we need to change bounds. When z is equal to 1, I have 1 equals tan theta. So what is theta going to be? How do I solve the equation 1 equals tan theta?
Is it pi over 4?
Good. This means the inverse tangent of 1 is theta, and the inverse tangent of 1 is indeed pi over 4. So my new lower bound is pi over 4. When I plug in e for z, and z is equal to e, I have e equals tan theta. There's no nice way to get that from your unit circle. Here, theta is just the inverse tangent of e. But that is our substitution with our bounds. Let's see what this integral becomes. We'll have 2 pi integral from pi over 4 up to the inverse tangent of e square root of tan theta squared plus 1. And then dz is secant squared theta d theta.
Don't we need to draw the triangle as well?
So if we were doing an indefinite integral, we draw the triangle. If we're doing a definite integral, we change the bounds. It never hurts to draw the triangle, but here we don't need to, although we will at some point at the end need a little bit of geometry. The triangle in trig sub is something we always do for indefinite integrals. And then for definite integrals, integrals with bounds, we just change those bounds. Remember what the triangle's for. The triangle's for going back to the original variable. When you're doing a definite integral, you don't need to go back to the original variable. That's the point of changing the bounds. Yeah, fair question, but not in this case. Other questions or comments so far? Okay. So tangent of theta all squared, that's tan squared theta. So I have 2 pi integral pi over 4 to the inverse tangent of e. Inside here, I have tan squared theta plus 1. What is that?
Isn't that secant?
Secant squared. Yep, and that's under a square root. So because tan squared theta plus 1 is equal to secant squared theta, that's the second Pythagorean identity. This square root is the square root of secant squared, which is secant. So we get 2 pi integral from pi over 4 to the inverse tangent of E secant times secant squared. Hey, it's everybody's favorite. You guys remember this old friend? This is why when I think it was Caleb suggested that we do integration by parts at the start. I was saying, yeah, that could work. Because how do you integrate secant cubed? It's a looping integration by parts problem. Now, I don't want to burn the class time, so I'll show you the setup here. We've done this enough back in chapter 7. I think we did this guy in class 2 or 3 times. This is a looping IBP problem. The choice of U and dV, you think of this as secant times secant squared, and you pick U to be secant theta and dV to be secant squared theta d theta. You would compute du and v from these, and then use a trig identity to make the integral loop. So I'm going to write down the result here. An antiderivative for secant cubed is 1/2, and I'm sure this will look familiar, secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. Close the absolute value. And we need to evaluate from pi over 4 up to the inverse tangent of E. So the antiderivative step here is quite challenging. We did a z sub and then a trig sub, and then the thing that comes out from the trig sub is the secant cubed integral, which we remember as one of those really hard integrals from back in chapter 7, where you need to run integration by parts, then do some amount of algebra to make the original integral show back up again. That's called a looping integral. At the end of the day, the antiderivative step here looks like this. You get 1/2 secant theta tangent theta plus the natural log of secant theta plus tangent theta. And if you don't remember how to do that, you should look back in your notes from chapter 7. This was 7.1. Or no, sorry, this was because we had IBP, but this was also in the trig section. I think this was probably 7.3 maybe. And there's also a bunch of videos, right, up in the modules. There's stuff from class and stuff from Patrick GMT. So if you don't remember how to do looping IBP, please refresh yourselves. These can show up here. The 2 and the 1/2 out front will cancel. And I'll have pi times, when I plug in my upper bound, that's secant of the inverse tangent of E times the tangent of the inverse tangent of E. I'm going to put some big parens here because we're going to have to subtract some stuff. Plus the natural log of the absolute value of the secant of the inverse tangent of E plus the tangent of the inverse tangent of E. And then from this, I'm going to have to subtract what I get when I plug in pi over 4. That's the secant of pi over 4 times the tangent of pi over 4 plus the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4. Okay. So not quite enough room on one line here. We plugged in the upper bound, and then we subtract what we get when we plug in the lower bound. Some of these things are easy to clean up. Some of them are a little bit trickier. Help me out starting up here. What is the tangent of the inverse tangent of E? Who can help me with this?
Wouldn't that just be E?
It is, yeah, it's definitely just E. And so that shows up in two places, here and here, both of which are E. The other ones that are easy, certainly the inverse tangent, the tangent of pi over 4. What is the tangent of pi over 4?
1.
Good. He shows up twice. One other thing that we should know right away, is the secant of pi over 4. What's that?
Two over root 2.
Good. 2 over root 2, which is another way of saying root 2. Right, so cos of pi over 4, we all remember, is root 2 over 2. But maybe you didn't know, or maybe you forgot, this is just a nicer way of writing. Some people would argue not nicer, a nicer way of writing 1 over root 2. If you rationalize the denominator here, you get this, which means that the secant of pi over 4 is the reciprocal of this. You could write it as 2 over root 2 if you wanted to, but it's much nicer to just call it the square root of 2. Because that's what it is. So what do I have here? Putting in the pieces we know, this piece is the square root of 2, and this piece is the square root of 2. So my surface area is pi times, I still don't know what the secant of the inverse tangent of E is, but we're going to figure that out. Then we have to multiply by E plus the natural log of the absolute value of the secant of the inverse tangent of E, still need that, plus E. And from this, we're going to subtract, I'll distribute this negative now, I'm going to subtract root 2 times 1. And we're also going to subtract the natural log of the absolute value of root 2 plus 1. So all that remains is to sort out the secant of the inverse tangent of E. These make for really good problems in trig class. But by the time we get to the end of Calc 2, you may have forgotten a little bit how to handle that. Does anybody remember how to find a nice algebra expression for this? Let me give that piece a name. The inside here, the thing I want the secant of is the inverse tangent of E. That's a weird number. That's what's causing me trouble. So let's just label it phi. Well, this means that E is equal to the tangent of phi. So the tangent of phi is E over 1. I can interpret that as an opposite over an adjacent and draw a triangle. So when I said we don't need a triangle at the start, but we will need one eventually, this is where we need it. And if you drew the triangle at the start, you could employ that triangle here, although it wouldn't be direct. You'd have to plug some stuff in. Tangent of phi is E over 1. So the opposite side I label as E. The adjacent side I label as 1. And then we use the Pythagorean theorem to complete the triangle. I know that this side squared is equal to this squared plus this squared. So this guy is the square root of this squared plus this squared. This is the square root of 1 plus E squared. Now that we've completed that triangle, we see that the secant of the inverse tangent of E, that's just the secant of phi, right? Because phi is the inverse tangent of E. That means I want the secant of this angle here. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. So this is the square root of 1 plus E squared, which is definitely not the same thing as 1 plus E, right? Square roots don't play nice with addition or subtraction. So here's our kind of little embedded trigonometry problem that will finally let us write down the answer in a nice format. The secant of the inverse tangent of E is the square root of 1 plus E squared. So we have root 1 plus E squared times E plus the natural log of the square root of 1 plus E squared plus E minus the square root of 2 minus the natural log of root 2 plus 1. The inside of these logs are clearly positive. You could lose the absolute values if you wanted and write them as parens. Either way is okay with me. And that's the surface area. Pretty frightening expression, but not impossible. And every step along the way is something that you've done before. So I'm going to give you a second to sort of assimilate this. There's quite a lot here. I'll move this down so you can see as much as possible. Here's everything from the secant cubed on. Take a second, check your notes, make sure you've got everything you need. If you have questions, now is the right time.
Is this like one of the hard easy problems, or is this like hard?
This is middle of the road. Hard here means impossible, right? There are plenty of surface area integrals, plenty of integrals in general, where we just can't do it, right? Without expanding the thing as a power series or resorting to some trick that involves infinitely many steps. So the fact that this is manageable, the fact that there is a nice antiderivative here, means it's not like a hard problem, but it's certainly not an easy one either. This is a little tougher than something I would put on an exam. I wouldn't make you do a Z sub followed by a trig sub followed by a looping IBP followed by some weirdo trig stuff on a test. That would be too much. Certainly this is fair for like homework, but on a test, I wouldn't, maybe the first two pieces, right? If you didn't have to do the looping IBP and then this weird bit of trig at the end, if it was just like Z sub and then trig sub and the trig sub integral came out nice, that would be about the level of difficulty for a test, something like that. Okay. Any other questions on the problem we have here? All right, I want to look at one more example before I let you guys go today. Last call for questions on this. Do we want to see the first few steps here? Coming back, here are the first few steps before the secant cubed integral. Okay. So the last example I have here for you is another kind of horn-shaped problem, and this one is quite famous. Has anybody heard of Gabriel's horn? So I'm not an expert on theology, but I think Gabriel in Christian theology was an angel of some sort, and his horn, which is like a large trumpet, was a an intimidating figure in the Bible. There's a mathematical object called Gabriel's horn. Is the solid generated by rotating the region bounded by y equals 1 over x for all x greater than or equal to 1 about the x-axis. And I'd like to ask two questions. Is the volume of Gabriel's horn finite? And is the surface area of Gabriel's horn finite? So we can take a look at one of those volume problems from the beginning of the semester, but see it in the context of a convergence question. And then we're also going to set up the surface area integral and see what we can do for that. And that will also be an improper integral. So both of the integrals here are going to be improper because the region we're looking at is everything under 1 over x from x equals 1 all the way out to infinity. In other words, the picture here right, here's the graph y equals 1 over x. I'm going to start at x equals 1 and then go all the way out. So sort of here's my region. It continues on and on forever. And I want to rotate that about the x-axis. So the resulting solid is this infinitely long horn. It gets narrower and narrower as you go further and further out. That's the shape we're looking at. Can everybody kind of visualize what it is we're playing with here? This is the solid that we get by rotating this region about the x-axis. And I let it go on and on forever to the right. This region extends forever to the right, getting thinner and thinner and thinner. So the horn extends forever and ever and ever to the right, just getting thinner and thinner and thinner. We've asked two questions. Is the volume finite? And is the surface area finite? So I'd like to set up an integral representing the volume. And the way we do this, of course, is as an as an improper integral. We can use the disk washer method. So if I come in here and draw my little strip perpendicular to the axis of rotation, where this is taking place at an arbitrary x value between 1 and infinity. This point up here is x comma 1 over x. So in part A, my dv is pi times capital R squared minus little r squared times dx, which is pi times 1 over x squared minus 0 squared dx, because there is no gap between my strip and the axis of rotation. The little r there is 0, and big R is always the distance from the further end of the strip to the axis of rotation. So this means that the volume of Gabriel's horn is the integral from 1 to infinity of dv, which is an improper integral. It's pi times the integral from 1 to infinity of 1 over x all squared, or just 1 over x squared dx. So is this finite? Here we're computing the volume.
Isn't it a p integral?
Very good. Yeah, this is a p integral. So this is a convergent p integral. Here, p is equal to 2, which is bigger than 1. That's how we get the convergence. And if we wanted to, we could actually evaluate this. Remember the way we do this. This is pi times limit r to infinity integral 1 to r, right? That's how you handle the type 1 integral. And then 1 over x squared, that's x to the negative 2 dx. So this would be pi times the limit as r goes to infinity of negative 1 over x evaluated from 1 to r, right? Your antiderivative here would be x to the negative 1 divided by negative 1, which is this. So we get pi times the limit as r goes to infinity of, when I plug in my upper bound, I get negative 1 over r, and then minus what I get when I plug in my lower bound, which is negative 1. Finally, as r goes to infinity, the 1 over r goes to 0. So you get 0 minus negative 1, which is just 0 plus 1, which is 1. So this is pi. In particular, the volume is finite. Isn't that strange? This thing's infinitely long. Think of it, it's like a trumpet that's infinitely long, but it has a finite volume inside. So if you sort of stood it up on its end and started pouring in water, it would eventually fill up. Think about that as I set up this next calculation, and this will be the last thing that we do for today. So the answer in part A is that the volume is finite. In fact, we can calculate it. The volume was pi. And we did that using the disk washer method. To calculate the surface area, for part B here, I first need ds, which is the square root of f primed of x squared plus 1 times dx. And remember, f of x here is 1 over x. So f primed, the derivative of x to the negative 1, is negative 1 x to the negative 2, or negative 1 over x squared. So this is what will go in here. And that means that my surface area, which would be the integral from 1 to infinity of 2 pi f of x, which is 1 over x, times ds, which is the square root of f prime squared plus 1 dx looks like this. And we can clean this up a little bit. This is 2 pi times the integral from 1 to infinity, 1 over x times the square root of 1 over x to the 4 plus, oh, sorry, there should be a square here. Yeah, sorry. It's a square here, because the derivative f prime is 1 over x squared, negative 1 over x squared. And when you square that, you get an x to the 4 plus 1. And then our dx at the end. So I want to take a second, make sure everybody followed the calculation that led to this integral. And then we're going to talk about the convergence of this integral in our last few minutes. Do we all see where all the pieces are coming from? My boundary function here is f of x. So his derivative, f primed, is negative 1 over x squared. So I plug that in here for ds. F primed squared is negative 1 over x squared squared. That will give me this 1 over x to the 4. The 2 pi can pop out of the integral. F of x is 1 over x. Dx is just dx. So this is the surface area of Gabriel's horn. And if I wanted to evaluate this integral, my first step would be to write it as a limit, right? It would be the limit as r goes to infinity of the integral from 1 to r. But I don't want to evaluate this integral directly. I want to do something else. Looking at this, does anybody have a hunch as to whether it converges or diverges, this surface area integral?
I think it converges.
This piece on its own looks like it would maybe converge, if not for the 1, right? The square root of 1 over x to the 4. And if not for the 1, the whole integral here would converge. But with that 1, we're in trouble. So here's my observation. One is less than 1 over x to the 4 plus 1, right? This guy is 1 plus something positive. So this guy is bigger than 1. And if you take square roots on both sides here, you'll see that this is true. If you take a square root of something bigger than 1, you get something bigger than 1. This observation implies if I divide through here by x, or I multiply by 1 over x, this, which is, I'll call it star, and this is true for all x greater than 0. In particular, it's definitely true on the interval 1 to infinity. Which is where I need an inequality to be true if I'm going to use my comparison theorem, and that's where this is going. So this function that I'm trying to integrate is bigger than 1 over x. Why? Because it's 1 over x times something bigger than 1. This square root piece here is bigger than 1. Therefore, by the comparison theorem, for improper integrals, since the integral from 1 to infinity of 1 over x dx is divergent, it is a p integral with p equal to 1, which is not bigger than 1. It follows by star, by that inequality, that the integral from 1 to infinity 1 over x times the square root of 1 over x to the 4 plus 1 dx must also diverge. Hence, the surface area of Gabriel's horn is infinite. I know we're just about out of time, so I want to do one brief thing to recap this concept for you. It's kind of mind-blowing, and this is what I ran into my health food store hippie nut job screaming about when I was in community college. I ran in there shouting at a bunch of people who, again, could not have given less of a shit that there's an object out there which I can fill with a finite amount of paint. But then you take that same paint, it's impossible to coat the outside of the thing with it. In other words, there are containers, Gabriel's horn, which I could carry around with me, holding a finite amount of paint. But that finite amount of paint that the thing holds inside is not enough to paint the surface, which is somehow mind-blowing. Usually we think of volume as being growing faster than surface area. Surface area tends to scale with the square of the length, whereas volume tends to scale with the cube of the length. In other words, volume is usually like an order of magnitude larger than surface area. But here is a very strange object where the volume is finite and the surface area is infinite. So the surface area is much larger than the volume here. And that particular kind of joke or way of thinking about things, that you could fill Gabriel's horn with a finite amount of paint, but that paint is not enough to cover the surface, is a cute way of reminding ourselves that while intuition is good, it can sometimes run away from us. I've got just a minute or so left. Are there any questions about the convergence argument that we're making here? Does everybody see why this kind of starting point inequality is true? I know I promised you that you were done with series, but I never promised that you were done with improper integrals. Do we all see that 1 over x to the 4 plus 1 is always bigger than 1? Because you're starting with a 1 here and then adding something positive to it. Since this is bigger than 1, its square root has to be bigger than 1. And then you just multiply through this by 1 over x. That will give you this. The 0 I added in on the left-hand side, remember, is just a necessary part of that theorem for improper integrals. And it is true that 1 over x is greater than 0 for all x which are themselves greater than 0. So don't be surprised, don't feel bad if you need to go through this convergence argument a little bit more carefully by yourself. The video for this class will be up just as soon as I possibly can. It'll be a few minutes after class ends. And then next week, we're going to start talking about parametric curves. So we're going to solve this arc length problem and also the tangents and areas problem from earlier. But in a situation where x and y are independent of each other, not linked to each other by any direct formula, but rather both x and y come from their own variables, t. So rather than having x be a function of y or y be a function of x, they're both functions of time. If you get through this week's homework and you're bored or you want something else to look at, I can recommend that you read section 10.1 in preparation for next week's class. We'll begin doing stuff like this, where we graph parametric curves by plotting points, just like you would in a baby algebra class, but we will very quickly proceed to something else. So if you don't remember parametric curves and polar coordinates from your trigonometry and pre-calculus classes, I strongly recommend that you read section 10.1 before Monday. It's a fun section. We're going to enjoy lots of silly, cool curves. Make sure you finish up the homework on arc length and surface area that we have open right now. If you have trouble with anything, or if you want to meet up with me, I will probably be doing an extra office hour this Sunday. And I also have my normal office hour today from 2 to 3 p.m. Oh, wait, actually, I may have to stifle that. Yeah, I have a committee meeting today from 2 to 3 p.m. So watch for an announcement on Canvas. I'll be rescheduling today's office hour, but then also having an extra office hour on Sunday. All righty. Any questions for me before I let you guys go? Okay, then again, if you need to contact me, come by the office hours or send me a Canvas message or email. You guys have a lovely weekend, and read 10.1 if you happen to have time. That is it. I'll see you all on Monday. All right, I'm gonna go ahead and kick you out, Alex. If you want to talk to me, come by my office hour or send me a Canvas message. Joe and I are gonna chat for a minute. All right, Joe, what's up?
Hey, I was just going to ask you a couple of questions. So it seems like what you end up doing is you do the chapter 11 stuff before you do the surface area. Like, okay. Is there a reason? I mean, I saw, because this is my first time teaching Calc 2, and I saw that was an option. Is that basically so that you can do integrals like that when you get to these sections?
There's two reasons I do it this way. First, I need them to be familiar with the concept of convergence to talk about Gabriel's horn and other fun shit like that. But another big reason is that many of the arc length integrals are fucking impossible, right? I don't know if you played with those in a while, but yeah, they are. They're really fucking hard. And most of them, if you just start writing down a random problem, an arc length problem without thinking about it carefully, will require that you series expand the integrand in order to do it.
Okay.
So I like to have them work some problems involving ellipses and talk a little bit about Kepler. And to do that, I need them to do the elliptic integral of the second kind, which requires series expanding using that binomial series expansion, the Newton's one. And a few other places like that. I just like to have the series stuff under the belt before we get to these integrals that so often require series expansion. But I know some people do it the other way.
Because that was one that was one of the things I had to do when I was like deciding what homework problems and stuff. I kind of had to go through it and make sure that I threw out all the problems.
Yeah, anything like that.
Right. And then, so like typically, is that about the amount of students that you have show up and like the level of participation? Because it seemed pretty good.
That was a quiet class. They usually talk a little bit more than that, but that's about the same number of students. This class, I usually have between 15 and 20 actually show up on a given day. I record these lectures, so I post them on YouTube, and the kids all know that. And I think that has had some negative effects on attendance because they know if they don't come to class, they can still watch the thing on YouTube. But I hammer on them pretty often. You need to come to class so you can ask questions and be a part of the discussion. And I give them little things during class and only in that setting that that can be helpful on tests. So every now and then I'll turn off the recording and give a little special to something them. And I warn them when that's coming to try and keep them attending. But it about normal today on attendance, a little less than normal for participation.
Okay. Yeah, because I was kind of wondering because there was at least one student, I don't know if you noticed it, but kept coughing.
I did.
So then that's good. And then that's when finally someone asked, can you turn off the mics?
Yeah. And normally I have Zoom set to automatically mute mics at the start of the meeting. I don't know why. Yeah. So that person must have manually unmuted themselves. And then proceeded to cough into their mic.
Yeah, it might have been that they were asking a question and did that.
I think that's right. They probably want to say something and then just left it off mute.
Yeah. And that, I think, and last thing.
Yeah.
So you were kind of doing exactly what I did last spring for my Zoom calls, is I just wrote had basically a camera and I just wrote on a piece of paper. But then what was that program that you had that you could kind of highlight with your pointer?
Yeah, I like this a lot. This is QCam, QCamera. So
how do you spell that?
It's the letter Q. Oh, here, let me just turn on my screen share. It's the letter Q followed by the word camera. It's this software right here.
Okay.
So when I got the document camera, I got from Santa Fe after we like shut down and had to do everything at home. And I was working on
Right.
my whiteboard for a long time, but it wasn't like, it's hard to read the whiteboard even with the fancy webcam and markers die and all that shit. So I switched to the
Right.
doc cam. And then when I went to download the drivers for the document camera, I just searched like QD 3900 drivers. And this whole software package is what came up. And that's nice. That I love that I can
Yeah.
like drag around and highlight stuff.
And then you said that, and I think I saw this from an email that like one of those massive email threads in the math department. So then you're basically using this program, you're saving this to your own computer, and then you're uploading it to YouTube, as opposed to having Zoom like process your.
The cloud recordings on
video.
Zoom are so bad, but when I
Right, yeah,
record locally, when I set it to record on the local computer, there's like no glitches, there's no like buffering or audio issues. The video is really crisp. I like this much better.
Right. Yeah, because I mean, so I'm only doing online classes. I just do a screen record and do the same thing as I put
Yeah.
that up on YouTube. But yeah, that was one thing that like bothered me a lot.
It was so bad. Yeah,
Yeah.
I remember, I hated it. And I
Well,
wouldn't
and not
realize
only did
until the kids
not
told
only
me,
did it-
oh, this recording stutters at like 10 different places. So
Well, and not only that, I remember having a bunch of students say that then the actual videos, even when I finally got them, they were blurry anyways,
Yep.
and they weren't very helpful. So yeah, that was, I was just kind of wondering about that.
This will record in full resolution on your computer, because when you're recording to the cloud, it can only record at the quality you can upload. And all of our upload
Okay.
speeds at home are way slower than download speeds. We get like 40 megabits per second down, but maybe 5 or 10 megabits per second up. So we can stream
Okay.
good video, but we can't broadcast good streams as well. So if the broadcast is laggy or glitchy or blurry or low resolution, then that's what we'll record on the cloud. But if you record locally, you'll get a high res recording that you can then upload slowly, to YouTube and keep all the quality. So I like that much more.
Okay, cool. Yeah, because I was basically taking notes throughout the class while I was just watching that. And yeah, those are a couple of things that I wanted. If I've got more email or questions, I'll email you about that.
Sweet.
But if I remember right, your evaluation packet is going to be due like at the beginning of February or something like that, right?
I think Katie likes to have the first copy available for review sometime around the second week of January. But then I don't think we need all the letters until the final packet is due. Let me check and see when that is. Last year it was in February. But
No, that'll be fine. I'll get it to you before this semester is done.
Okay.
Yeah, I mean, I'll probably be writing it here. I mean, I don't know when, but yeah, I'll do that. But yeah, I mean, I remember doing that. And you might be right that they're due in January, and then I wouldn't be like voting on it until like February or something like that.
I think it's something like that. Yeah, I don't remember the
Okay.
specifics though.
Okay. Well, yeah, I mean, I've got some time. I'll make sure I get that to you, and then we can go from there. And like I said, if I've got more questions, I'll let you know.
Okay. Yeah.
But yeah, I'll let you get to that next meeting you got.
All right. Thank you, Joe. I really appreciate you doing this. It means a lot to me.
Yep. No worries. I went through the same stuff. I know what you got to do.
I feel you. Yeah. All right.
Yep.
Thank you.
Have
man.
fun. See you, John.
Bye.
Yep.